Okay, thank you. Uh, so good morning once more. As one of the last stages of our Olympiad, I was asked to deliver some kind of lecture or scientific talk on the things in astronomy that I'm mostly interested in gravitational waves, black holes, and the last Nobel Prize in Physics of this year. The lecture will be in English. I think that won't cause problems for Russian participants, I hope, but no other options. Okay, so my name is Илья Oрлov. I'm Deputy Director of Novosibirsk Planetarium and Assistant Professor of Novosibirsk State University. And I teach astronomy, physics, and many other subjects, both here in Planetarium and in Novosibirsk University. So, strange words, gravitational waves. But let's start from some historic words. Okay, не хочет. I say click. Oh, wow. Three wonderful men, Rainer Weiss, Barry Barish, and Kip Thorne, especially known as Kip Thorne, the Nobel Prize laureates of this year, of 2017, in physics, for their discovery of what we call gravitational waves. A wonderful picture of something hot, dense, massive, and rotating. And such the accelerating masses cause the propagation of some kind of waves inside the space-time matrix. That was predicted more than a century ago by Albert Einstein in general relativity, but since the very last years, since last 10 years maybe, no direct evidence of the existence of gravitational waves was ever discovered. But everything changes. Starting from the history of mankind, from history of astronomy, if we come to under the night sky, outside the city, what do we really see then? The question may seem silly, since that's obvious answer, that we see the planets, the stars in constellations. Yeah, say hello to observational round. Yeah, constellations. There were some problems, yeah. Nebula, galaxies, even far galaxies, and many other objects that shine in the night sky. But in fact, no. In fact, we do not see directly the planets, the stars, and the galaxies. But what do we see? Yeah, we see just the light from them, the electromagnetic radiation. The light emitted by the hot surface of stars and other objects and propagating through the space and time. The light is the oscillations of the electromagnetic field of different kinds. We call them the electric field, the magnetic field if the charges are moving, or for accelerating charges, strange word, synchrotronous radiation. But anyway, the electric charges move and, and create the electromagnetic waves that we do see. We don't see planets, we see just light. We don't see stars, we see just light from them. And of course, light is running at speed of light. Yeah, that's obvious. And since the very early ages of humankind, maybe something like hundreds of thousands of years, when the people firstly gaze at the sky and see that light coming from planets and stars, since that early ages up to the maybe 1930s or something like that, the electromagnetic astronomy, the astronomy based on the light that stars emit and we consume, and we see was the only type of astronomy available for the humankind. No other options. Just look at the sky and see the light. And this light comes from the radiation from a heated surface. So we do not see the internal structure of the celestial bodies. Yeah, we see just the temperature of their surface. Yeah, and no other information is available to us via the electromagnetic astronomy. And other strange thing that from all of this electromagnetic spectrum, we see just this small part, yeah, just the visible light. We don't see here, we don't see here, just very narrow band of the electromagnetic spectrum. And that's not good. We want to see here, we want to see there, we want to see not only the light, but other radiations, other type of radiations. And the magic date, 1930s. Do you know what happened in the 1930s? Huh? Radio, yeah. Yeah, that type, that side of the electromagnetic spectrum. Radio waves astronomy, radio telescopes, radio detectors, and we started to see the light not only by our eyes, but in that side of electromagnetic spectrum. That light is caused not by the heated surface. It's caused by the electrons, the charged particles, accelerated by electric and magnetic fields in the universe up to the speed of light, or almost to the speed of light. They are very fast. Almost the maximal available speed in our universe. And the universe is much more active in radio waves and in microwaves than in the visible spectrum. Yeah, in the visible spectrum, the universe is almost stable. The new stars, the nova stars, appears very rarely, and planets go as they are predicted to do. Yeah, the star sky is absolutely stable, at least it seems. And in the radio astronomy and in the radio spectrum, we see the active galaxies nuclei, the direct consequences of the Big Bang. So the much more active processes in the universe. The universe is not stable; it's actively developing, and the objects in the universe are also actively developing. That was strange. That seems strange. Very soon, from the radio astronomy, we come to that side of the electromagnetic spectrum, the X-rays and the gamma rays, the gamma astronomy. And the universe appears even much more wonderful in gamma rays. We look at the solar flares. The sun is the source of X-ray radiation and gamma ray radiation. The stellar afterlife, meaning neutron stars, the radiation from nearby black holes, thermonuclear processes in the stellar cores. So we started to get information not only on the heated surface of the stars and other objects, but from the internal structure, from the stellar cores. But still, that's only the electromagnetic astronomy. That's just the light, not the visible light, but it's the light. And what are the next steps? We don't want to see only the light. There are many other particles and radiation types in the universe. So what are the next steps? Two next steps were proposed in the first half of the 20th century. But direct detection of this radiation and these objects were made a little bit later. The first proposition was the neutrino astronomy. The neutrino is the tiniest particle in the group of elementary particles. It has almost no mass. It propagates at the speed of light, almost on the speed of light. And it penetrates the Earth entirely. So it can come through all the Earth without any interaction with any other particle. So it seems that if we manage to catch these tiniest particles, we can get the information from the very internal structures of the stellar cores, of the active objects in the universe, and the neutrino source are the thermonuclear processes. So that's very interesting. That ones that we cannot see absolutely in the visible light and the electromagnetic radiation. Again, the universe should be much more active in the neutrino rays than it is in the invisible rays or in any other sides of electromagnetic spectrum. The main sources are the sun, other stars, active processes in the galaxy nuclei, in the stellar remnants, and there should be a cosmic neutrino background radiation emitted some seconds or minutes after the Big Bang, and it still propagates through the universe. It would be very interesting to catch it and to see how the universe, entire universe, was formed and what were the structure of the universe some minutes after the Big Bang. There is no other sources of information on this epoch except for neutrino astronomy. But there are very hard technical difficulties. If the neutrino can penetrate through the entire Earth, through the entire planet, how can we catch them? That's a problem. But this problem is somehow being solved in last decades with promising success. Another proposition made, as I said, by Albert Einstein, the gravitational astronomy. The gravity is the main force of the universe. Everything takes part in the gravitational interaction. So it would be very interesting to see the gravitational structure of the universe. Not the electromagnetic as we see, but the catching gravity waves. Gravity waves are very small in magnitude, yeah, and significant gravitational waves, magnitude of gravitational waves can be caused just by superactive events, collision of galaxies, collision of neutron stars, collision of black holes, the birth of new stellar remnant, of new neutron star, of new supermassive black hole. And that's super interesting, I think. Okay, what are the gravitational waves? Yeah, a good picture. There are not the waves in the medium caused by the gravitation. Yeah, if we look at the surface of sea, of the ocean, there are always some waves caused by the gravitational interaction of the water with the Earth. Yeah, that's not the gravitational waves we are talking about. Yeah, that are the waves of the gravity itself, or as it's said in special relativity and general relativity, waves of the curvature of the space-time. If we put in the space the massive body, the dense massive body, it curves the space-time. The straight line is no more the straight line, yeah, and some more strange and weird events and objects appear. The source of the gravitational waves is rapidly accelerating masses. If the star, for example, just resides at the space and doesn't move, there are no gravity waves. And even if the star is moving at a constant speed, there are no gravity waves. But we need accelerating masses. The more the better. Yeah, we need dense, massive objects accelerating very rapidly. For example, rotating one around the other. Gravitational waves should run at the speed of light. Nobody have ever measured yet. But the proposition is that the speed of gravity waves is the speed of light. At least they couldn't propagate faster. And interesting things about the frequencies of the waves. The frequency is the main parameter of all the waves. Both electromagnetic spectrum, radio waves, sound waves, the waves of the surface and the sea, all other waves are determined by their frequencies. A typical frequency for the electromagnetic waves, for the light that we see, for the X-rays and other sides of the spectrum, is 10 to the 7 up to 10 to the 20 hertz oscillations per second. Yeah? And an interesting thing is that the gravity waves' typical frequencies lie in the completely different range. Yeah, it's 10 to the minus 9 up to 10 to the 4th hertz. So that is not like the electromagnetic radiation waves. Yeah, what waves in our life, in our common life, have such a frequencies? Do you know? Okay. The typical frequencies of some hertz to some kilohertz is the sound waves, has the sound waves. Yeah? So, and the sound waves are the waves in the medium, waves of the density in the medium. And so the gravitational waves in the curvature of space-time are more like the sound waves than the electromagnetic radiation. Yeah? So waves of the density of the space-time. And they really lie in the same frequency range. Something like a sound of a space-time. Interesting picture. Yeah, that's a computer modeling, of course, computer simulation, on how the gravitational waves should propagate through the space-time. Yeah? Without any gravitational waves, without any oscillating masses, the space-time should be absolutely symmetric. Yeah? And these curves should be ideal circles. Yeah? But from there, the gravitational waves is being propagated. Yeah? And the ideal circles transform into something stretched, yeah? Into the ellipses. The speed is the speed of light, of course, so not so slowly. Yeah? But the main idea is as follows. What can be the sources of the gravitational waves? As I have already said, we need something massive, something dense, and something rapidly rotating. Either orbitally rotating, either rotating around itself, around the axis. Yeah? The pulsars. Yeah. The pulsars were discovered in the beginning of the 20th century. It can be said that they are well-known stellar-like objects. At least we know many of them, and we get many information on them. So pulsar is a rapidly rotating, hot, dense neutron star with a frequency of rotation of 1 Hertz to 1 kilohertz, the same range that we need for the gravitational waves. Yeah, the kilohertz pulsar is something weird. Yeah, the star oscillating on 1,000 rotations per second, but it can be. It appears it can be. They have very unstable surface. That's not a good stable star like our sun. Yeah, the surface is the surface is strange. Yeah, due to magnetic hydrodynamics and surface deformations due to very rapid rotations and some other strange processes of astrophysics. And really, they should emit gravitational waves of double rotation frequency. If the stars rotate with 1 Hertz frequency, 1 rotation per second, it should emit the gravitational waves of frequency of 2 per second, of 2 Hertz. Another interesting sources are the double systems with orbital rotation and orbital accelerations of hot and dense objects. For example, double white dwarfs. Yeah, they are quite hot, quite dense stars, but they are small. They are less than our sun by mass. Yeah, better are the double neutron stars. Yeah, they are denser, hotter, and more massive. The ideal situation is double black holes, the most dense objects that we know, or something combined. Yeah, neutron stars rotating around the black hole. Yeah, the white dwarf and a neutron star, some combination of dense, rapidly rotating objects. And such systems should have a significant energy loss due to gravitational waves emission. And if the double system constantly lose its energy, the periods should fasten, the rotation should fasten, and the distance between the components should shrink. They should be closer and closer and closer to each other. And that can be observed, at least theoretically. And the final stage is the merging of the objects. Yeah? One object fall to the another one. Yeah? They combine and form something more interesting and maybe more strange. Yeah? So during their life during the life of double system, it should constantly emit the gravitational waves. Yeah? When the objects come closer to each other, the magnitude of the gravitational waves rises. And during the merging, the accelerations are enormous and the masses are huge. So we have a signal, yeah, of the magnitude maybe 10 times larger than the magnitude here. And that script may be discovered and detected. Where can we find such systems? A promising place for dense double systems are the galaxy centers. In the center of our galaxy is what? The black hole. A supermassive black hole with a mass of at least 100,000 of masses of the sun. Maybe more, maybe 1 million. And around it, some stars are rotating with the orbitation periods of months, or maybe weeks, or maybe days. Much faster than our sun rotates around the center of the galaxies. And the accelerations are enormous, and the star masses are quite large. And we can hope that if looking at the galaxy center, we can detect the gravitational waves caused by the energy loss of such double systems. Yeah, the supermassive black holes, their rapid rotations with small periods and high velocities and accelerations. And of course, in the final stage of the lifetime of these stars, it falls to the black hole. These all factors cause the emission of gravity waves and energy loss, rotation energy loss. And that was simulated. At first, that was simulated let's take one star orbiting the central black hole of the galaxy. That's not the Kepler orbit, yeah? Since the general relativity and special relativity cause the orbital rotation to be not due to the Newton laws and the Kepler laws. There are separate laws of rotation around very dense, massive objects. Yeah, the orbit is something like such a flower. Yeah, and when the star is close to the central black hole, it emits the gravitational waves. Yeah, when it's far enough, the magnitude is not so large, but on the close distance, we can catch the gravitational waves. Really, this kind of systems the system of this kind was detected. It's called Hudson-Taylor double pulsar. It's the Nobel Prize in Physics in 1993, the first Nobel Prize on gravitational astronomy, just before the discovery, the direct discovery of gravitational waves. That's a notation of this pulsar. 1913 is not a year. Yeah. Two neutron stars. At least one component is a neutron star with a rotation period of 17 rotations per second, 17 hertz the rotation, and the orbital period of something slightly less than 8 hours. And of course, theoretically, this system should lose its energy and emit gravitational waves. And really, it was measured. The periods and the distance between components were measured with a high enough precision. For the scale, that's the diameter of the sun, of our sun, and that's the distance between the components. Yeah, and it was proved that the orbital diameter shrinks. It becomes closer to the companion star, and the only reason that can cause such a shrinking of the orbit is the gravitational waves emission. So that was the first system. For that, it was proved with high precision that it emits gravitational waves. But that was something like 20 years before the first direct detection. Yeah, that's a year of observation. That's a shift of the orbit. And the experimental dots, the experimental points, absolutely confirmed the prediction of general relativity, of Einstein general relativity. Moving further to almost nowadays, how the gravitational waves can be directly detected. Yeah, that's one of the first gravitational waves observatory, and one of the most successful ones. It's called LIGO, Laser Interferometer Gravitational Wave Observatory. They lose the letter W here. And it's composed on two interferometers, one in the Livingston, Louisiana, USA, and the another in Hartford, Washington, USA. So the distance is something like 4,000 kilometers between them. And every interferometer is some complex laser systems with lenses, mirrors, modulators, and so on and so on. But the main thing is that we have the laser beam of 4 kilometers long, of 4 kilometers length, and the other one another 4 kilometers in transverse direction. Yeah, and when the gravitational wave comes, for example, from the heights, yeah, it interacts firstly with this mass at one side of the laser beam, and then after the short period of time, but measurable period of time, with this mass. So this mass will move first, yeah, and that mass just after some delay, after some period of time, and that can be measured. So we constantly measure this 4-kilometer length with an unprecedentedly high precision of something like 10 to the minus 18th meter. Using the laser beams and optic interferometry, we can reach such level of precision. And we can, therefore, we can catch the gravitational waves of 10 Hertz to 10 kilohertz. So the one side of the gravitational wave spectrum. Yeah, something like that. So if the gravitational waves come from any direction, at least one of these 4 kilometers long beams will shrink and change its size, and then can be detected. And very soon after the launch of the complex, the first results appear. Frankly speaking, they appear just before the official run of the complex, before the opening ceremony, on the test beam, on the test 2 weeks of utilization of this complex. But on the February 11th, year 2016, the first result, the first signal, the first significant signal of the gravitational waves. What has happened? The two black holes orbiting each other merged. The first one is 36 masses of the Sun, and another one is 29 masses of the Sun. The mass of the final black hole is 62. And that may appear quite strange. 36 plus 29 is not 62. Yeah? It's 65. But 3 masses of the Sun was emitted, was radiated like a gravitational wave. So in the time period of something like several microseconds, the system loses 3 masses of the Sun in a gravitational radiation. That's enormous magnitude that cannot be caused by any of other systems. And that was 1.3 billions of light years from us. So this event occurred 1.3 billion years ago. And the gravitational waves have just arrived here to the Earth. And that graph is like the graph of previous slides. Yeah? Everyday common dull life of a binary system and the merging. Yeah? The merging is the most interesting thing here. Yeah, that's artist impression, of course. It's not a photo of merging black holes. Something like that. And if we are lucky enough, there will be the video. No. We are unlucky. Okay, no video. Yeah, please try. Yeah, that's the video. Wow. That's too slow. No, we are not lucky enough. So, 2 objects rotating around each other. And the most interesting thing is, of course, at the time 0.00, the merger, when 2 black holes are combined in something strange that we do not have any theoretical model of. We know that the black hole should be absolutely spherically symmetric. But if you try to combine 2 spheres, you cannot do it in a way that it's always a sphere. Yeah? There will be something intermediate, not a spherical. Huh? Yeah? It's good? Let's wait out to the 0. That's not good. Okay. But we do not have any theoretical prediction or theoretical explanations of non-spherical black holes. We do not know exactly what it is. It cannot exist due to the general relativity. Or maybe the general relativity is not so good theory for merging black holes. No, that's no way. Okay. And the merger of the black holes is one of the most intriguing objects of nowadays astrophysics and general relativity. We don't have an explanation yet. After the first success of the LIGO observatory, Hanford and Livingstone, new observatories are being constructed, built, and soon will come to the operation stage. In Europe, in Italy, Virgo, it's already operational. It combined their results with the LIGO, and I'll talk about it a little bit. LIGO India, the base of the interferometer will be as large as possible, combining the results from USA and India. The Japan laboratory Kagra and some other observatories are being developed, planned, and constructed. So we take first steps to the full gravitational wave astronomy. That's intriguing and promising. Yeah, and some other results. That's Virgo interferometer in Europe, in northern Italy. And it started less than a year ago. It started the operational stage, and from the very first steps of its operation, they combined the results with the USA LIGO observatory, and that provides very intriguing possibilities. Up to nowadays, we have something like 5 or 6 detections of the black hole mergers from LIGO Hanford, LIGO Livingstone, and Virgo. And, and we started to collect the observational data on the super high stellar masses of black holes. That's another strange thing. In the first detection of the gravitational waves, we detected the black hole with a mass something like 60 or 70 solar masses. The thing is that we do not know exactly how such an object can appear. We don't know how these objects can appear of black holes of 30 and 40 solar masses. We know for sure that in the final stage of the stellar development, of stellar life cycle, the black hole can form. Yeah. If this star is massive enough, something like 10 masses of the sun, it collapses to a black hole with a mass of some solar masses, 3, 5, 7, but not 30. We do not have the model of formation of supermassive stellar black holes. That's not a million solar masses like in the center of the Milky Way, but that's not 2 or 3 masses of the sun. We don't know how such an object can appear. Moreover, there was the first detection not so long ago, something like in mid-October, it was announced this year, something like a month ago, that LIGO and Virgo together detected the merging of neutron stars. 2 neutron stars with masses slightly larger than of a sun, combined into one neutron star, or maybe a black hole, that's not so obvious, of 2.5 or 3 solar masses. Up to nowadays, it's a unique event. We do not know how it can be, how how two neutron stars combine, and what processes are there. And so there's a complete zoo of the objects. The pessimistic Americans call the stellar graveyard. So that's afterlife of the stars. Yeah, there's a zone of black holes, of so-called electromagnetic black holes that can be detected not by the gravitational waves, and the supermassive stellar black holes that cause the gravitation emission. Yeah, that's a zone of neutron stars, and that's a gap between them. We hope that in this gap, the strange objects can be found, something in between neutron star and a black hole. But we completely do not know how it survives, how does it exist. That's the mystery gap between neutron stars and black holes. And maybe this merger of two neutron stars is the first object in this gap. That's completely new astrophysics, completely unknown. Another strange thing is comes when the LIGO or Virgo astrophysicists are asked where in the sky is that merger event. For the first event of merging of the black holes, that was a very strange answer on the questions where. Well, somewhere in the northern hemisphere. So we do not know completely. We cannot point in the sky that there it is. Yeah, the gravitational waves, the gravity waves came, and we do not know where it came from. When the results of Virgo were combined with the results of LIGO, the precision was much better. The last object, this object, is, if I correctly remember, somewhere in the constellation of Cepheus. Ooh, okay, not the northern hemisphere entire. Yeah, it's much better. But the precision is yet low enough. We cannot point directly. That is the next steps to be done. So we cannot yet make a map of the sky in gravitational waves, but we urgently want to. That could be another map of the sky, not the radiational way. So, tired? I think yes. So what do we have for now? The results of our first steps of detection of gravitational waves. So the main results, they are detected. And that result is the most significant, one of the most significant in modern astrophysics and cosmology. The Nobel Prize, yeah? It deserves. And for the first time since Newton, we directly prove that the gravity propagates not instantly. So the Newton was wrong when supposing that if we move one body, all of the universe get known instantly of this moving. Yeah, the gravity propagates maybe at the speed of light, plus or minus. Yeah, plus would be strange, but still. We haven't found the controversies in general relativity, except for these merger objects. We do not know how it can be explained by the general relativity. But in the propagation of gravitational waves, in the development of double system, everything is fine in general relativity. So Albert Einstein was almost right. And we have done the first steps to the gravitational waves astronomy, first promising steps. And by the way, we have found the strange objects, the black holes, of extremely large but stellar masses. We do not know. We do not have the models for them. We don't have the models for their development and birth and their fate. We don't know what are they for. And we detected even more stranger objects, the mergers of black holes, the mergers of neutron stars, and for that objects we do not have any theoretical model. That's the urgent task for the theorists, for the astrophysical and cosmological theorists. And many more is to be found. So that's just the first several steps on a long way to the gravitational wave astronomy and to more deep understanding of what the universe is and what the universe is constituted from. And we urgently need the discovery of massive extreme objects and their interactions. And that's maybe the most promising branch of the science, of the modern science. Okay, thank you for your attention. I can answer your questions if you ask. And I would like to say at the last that we are absolutely interested and eager for collaborations both in scientific and educational events and developments. And we would be happy to collaborate and cooperate. Thank you. Please, your questions? Everything's clear? Yeah, thank you. Huh? Okay, thank you. That's a good question. Where is my first? Oh, yep. Of course, that can be done only by the models, the simulation. We haven't directly observed these objects, for sure. Frankly speaking, we cannot directly observe any black hole. Yeah, yet, not yet. And you can see that the precision here is quite bad. Yeah, so 36 plus minus 5. Yeah, that's 30 up to 40. Yeah? Like in your theoretical round. Yeah. Sorry. So that's not for sure. Yeah, that's not high precision calculations. Yeah, but that are the model numbers that fit with maximal precision. So that's just a model. Maybe everything is not like that. Maybe, but the probability is quite low. We have quite good models of the binary black hole systems, but we do not know what's the merger still. Mechanism of what? Single pulsar. Okay. Where is my pulsar? Not that pulsar. Oh my God. That pulsar, yeah. We need a dense object of quite a large mass with quite a large accelerations. And when the object with the mass of the star is rapidly rotating, the velocity of the surface is quite large, it's quite fast, and the rotational acceleration is quite large. And that's enough for emitting the gravitational wave, the gravity waves. Yeah? So the mass moves with an acceleration. It's quite enough. The magnitude of the gravitational waves should be several orders of magnitude lower than for the binary system. But still, theoretically, it can be detected. But still, up to nowadays, we haven't detected any gravitational radiation from such system. Maybe it's too small of magnitude for us to detect. That's not enough precision of our interferometers to detect such gravitational waves. But theoretically, they are possible. And Hulse and Taylor proved that the binary systems in the universe. No, that was a binary system, yeah. There is no direct detection of such a system with gravitational radiation, but that's a possible way of detecting. That's just a theory, yet. More questions? No? Yep. Okay. Just a moment. Ligo. That's it. This energy, the energy of their orbital rotation is many times less than the energy of the black holes itself. So the theory is, the proposition is that this energy is converted not from the orbital velocities, from the orbital energy, but from the masses of the black holes itself. The orbital rotation is quite fast, but it cannot explain such enormous energy. So they come from the internal energy of the black hole, and that's strange. Yeah, we still think that the black hole itself can emit nothing. Yeah, it's a black hole, but it appears that not in this situation. The strange thing is that the energy of the black hole is emitted, and that's the first case that cannot be strictly explained yet. That's another interesting thing. Yeah. Okay. The same system as what? I didn't catch. Sorry. Michelson-Morley. Okay. It's something very similar. Yeah. The Michelson-Morley experiment was designed to detect the ether in the beginning of the 20th century, and maybe if they could improve their precision of something like 15 orders of magnitude, they could detect the gravitational waves. Yeah, the system is very similar, of course, but the problem was that they do not have such lasers and such a precision instruments of measurement. Yeah, the systems are very alike. Yeah, sure. Just a moment. Oh, that's a hard question. I'm not so a specialist in pulsar physics. I cannot answer this. I don't know. I need to read some papers on this. That's a good question. Due to the general relativity and special relativity of Einstein, no signal and no body and no information can propagate faster than light. The gravitational waves is surely a signal, an information on the accelerating moving of massive bodies. So if the Einstein theory is right, nothing in the universe can travel faster than light, even the gravitational waves. But the Einstein theory may be not so right. Yeah, it can be so. But we do not have yet any direct measurements with suitable precision of the speed of the gravitational wave. All measurements we have made shows that the speed of gravitational waves is the speed of light plus or minus something. Yeah, and that something is quite large. So we do not know for sure. But if the gravitational waves can travel faster than light, that means that the whole general relativity theory is not so right, is wrong. And maybe we would have some more direct observations of the violation of general relativity, and we do not have them. But that's a promising question. Of course, more precise measurements are to be made, and we should improve the precision of our instruments. We don't have the strict answer, the precise answer of this question. More question? Mm-hmm. Oh, that's a hard thing. Yeah. In a particle theory, there is a special particle called graviton that should be responsible for the propagation of gravitational waves. Yeah. And in the particle theory, in the particle physics, the properties of this graviton are proposed. Yeah, the spin number, the mass of 0, and so on and so on. But I think that the detection of gravitational waves is the first step to the direct detection of graviton. Yeah. But still, up to nowadays, we cannot combine the theory of quantum physics with theory of gravitation. It's a great challenge for the theorists, yeah, to design, to develop the grand unification theory that should explain every interaction: electromagnetic, weak interaction, strong interaction, and gravitational interaction. We do not have the complete theory yet. And maybe the detection of gravity waves, detection of graviton, well, maybe particle physicists will participate in these experiments and tell us something new about the gravity particle, but not yet, unfortunately. Again, we do not have such a precision yet. That's just the first steps. Mm-hmm. Yes, something like that really happened. Since just before the merging of the black holes, they have enormous acceleration, and after the merging, that acceleration disappears. Yeah. So this large signal, this large emission of radiational waves, is the enormous fast loss of the energy due to energy conservation law. There was the orbital energy, there was the energy of two black holes. They combine. The total energy of system decreases, really, on the three masses of Sun. And this decrease in energy is emitted like a gravitational waves. So we do not have the violation of conservation laws. Yeah, conservation laws is main, the major. So everything is fine with conservation laws. Yeah. Mm-hmm. Mm-hmm. Really something like that sound waves. And the physicists from LIGO, just several days after discovery of the first merging event, published a real sound file. In the internet it can be found. The real sound of this event. they even do not convert in the suitable frequency range. It is already in that range that is suitable for our ears. It's something strange sound file, but it can be found and listened. How the merging black holes whistle. Okay? Да, окей, хорошо. Okay, I was asked to say that just after the election, meaning just now, you'll be presented a full-dome film, The Phantom of the Universe, on the dark matter discoveries, another interesting thing, another not so clear things in modern astrophysics and cosmology. So, if you don't have any questions, then thank you for your attention. They were very good questions. It was a pleasure for me. Thank you.